Because he's only participant? No, he's co-organizer. Good morning, everyone, and welcome to our webinar this morning. We'll just give it a few seconds to allow everyone to enter the webinar. So as it is 9 o'clock, welcome to this webinar this morning called What's Next? A Shift to Electric and Efficient Net Zero Industry. We have been organizing this webinar with our great partners here today with us, also joining us as speakers in a moment. So I'm happy to introduce, first of all, our own association, the European Heat Pump Associations, coordinating this webinar, the voice of the European heat pump industry in Europe, promoting sustainable heating and cooling solutions to support the energy transition. With us today, we were very lucky to get on board KCORC, which is the knowledge center of Organic Rankine Cycle, who will today present to us this technology and innovation to decarbonize industries. In addition, we were very lucky as well to collaborate with the European Climate Foundation, which is a philanthropic initiative supporting policies and partnerships to drive Europe's transition to a low-carbon economy. Without any further ado, I would like to present to you our agenda today, which will go as follows. So we will be receiving quite some nice presentations with great, excellent speakers. We have 2 keynotes and then case study presentations that will go more in depth into the techniques of heat pumps and ORC. If you have no clue what they are, no worries. This is what this webinar is about as well, and you will soon find out all about them. We will also continue afterwards with the Q&A, and this is your chance to let us know if you have any thoughts or questions to the speakers. So you have a Q&A little logo up on the left of your screen that will allow you to enter a chat. You can type your question, you can upvote other questions that you like, and the speakers will happily answer you in written in the chat directly. If you would still like to ask a question orally, you can also wait for the end of the webinar for the Q&A session and here enter and ask your question orally. During the Q&A session and after answering all your questions, hopefully, we will also have a live Slido to check out a little bit your thoughts and what you've learned about this webinar today. So, as you know, industrial heat is one of the biggest sources of greenhouse gas emissions, making up almost 2/3 of all industrial energy use. Tackling this challenge is essential if Europe wants to reach its climate goals, strengthen its energy independence, and stay competitive. One of the main ways forward is the electrification of heat in industry. By replacing fossil-based heating and energy with clean and efficient technologies like organic rankine cycles and heat pumps, we can make industry's energy sources clean, efficient, and resilient, while cutting emissions and shifting the industrial vision to an electrified one. So many things are going on, as you know, on the political spectrum, but also on the innovative spectrum. This morning, for example, in the German parliament, there is an open hearing on gas storage levy and consumers' protection. So let's turn to Germany to start a discussion on the innovative side for sustainable heating and cooling solutions for industries, namely efficient process heating, to put an end to gas and contribute to a successful implementation of the electrification action plan. So I would please like to invite here with me Christian Noll, a general manager of DENEFF. DENEFF is Deutsche Unternehmensinitiative Energieeffizienz, which is basically the German business initiative for energy efficiency, a network of companies and organizations in Germany promoting ambitious energy efficiency policies and market solutions. So I'm just calling up here for Christian to join us. There you are, Christian. Thank you for joining us. So you are the co-initiator and founder member of DENEFF. Before co-founding DENEFF 15 years ago, you, the communication graduate, worked as an energy efficiency campaigner for the German Federation for the Environment and Nature Conservation. Prior to that, you gain PR and campaign experience as a freelancer for NGOs and communication agencies. And this morning, you're going to introduce to us the missing puzzle piece of industrial decarbonization, which is efficient process heating. Christian, the floor is yours.
Thank you, Rachel. Good morning, everybody. And thanks, Rachel, for perfectly summing up the key messages. And I'm very happy to dive a little bit deeper in why it is so key to talk about the decarbonization of process heating, because so at least in Germany it's the case, and maybe you can confirm this from your countries. When we are talking about the industry, we are just talking about cement, about steel, and all the hard-to-abate sectors. And when we are talking about heat transition, we're just talking about the residential heating sector. So this is why we say this is somehow the forgotten half of the heat transition. Yes, I'm very happy to highlight a little more what are also the opportunities to be grasped here for not only climate transition, but also for our economies as a whole. Can you please click one slide further? I don't have the controls yet. So the first point is it is regarding everyday products in our lives. Second is that for most companies, becoming climate neutral primarily means to decarbonize their process heat. There's also an opportunity to halve the energy demand for the industrial sector and cutting the bill of our German industry by 2.1 billion euros per year. That's the case for German companies. And if you transfer it to the EU level, you could approximately just multiply it by 4, and then you have a notion what are we talking about. There is an opportunity, of course, for all European manufacturers. There's enormous market potential. I'm happy to show you some research we've commissioned on that. Still, this is a field where we have to strategically secure our competitiveness in Europe from our manufacturers in this field. So to prevent to happen what happened to the PV industry to not happen again. I'm also happy to make it a little bit more imaginable for you, to show you some frontrunner projects which show that decarbonizing process heat is possible. They've done great success and have great plans for the future. But in the end, if we want to become those lighthouse projects a standard, politics have to act now. This means we have to implement the energy efficiency first principle, and we have to tackle the barriers of process heat transition I would like to highlight then in the end. On DENEFF, we are Germany's voice on energy efficiency. We are the voice of 250 pioneering companies. From technology manufacturers, consultants to financiers. Of course, we are closely following politics in Germany, also on the EU level. But what we're also doing is in innovative projects to develop new solutions. For example, we had a big project 5 years going on waste heat recovery from data centers. And now one field, or the most important field of our work in the industrial sector, is process heat. Next slide, please. Yes, as I started, we have many products in our daily life, and they have one thing in common. To produce them, this requires process heat. So we've marked down some examples about the ranges of temperatures and different range of temperatures required to produce paper, plastics, metal, food, glass, beverages, and many more products you can imagine. And this different temperature levels will play a role in what I will highlight later on. So keep it in mind. We're talking about very different level of temperatures, which are then a key question on when you're talking about how to decarbonize that. Next slide, please. Again, and as I have said before, for most companies, the biggest part, and that's 75% of their greenhouse gas emissions, stem from their own side, from heat application. Most of the companies don't have process emission, like cement, for example. So for them, it's all about process heat. Of course, they will in the end have other emissions that can be solved by strategic procurement. And energy efficiency plays a key role here to make the transition affordable by lowering total energy demand, but also temperature levels. When you, for example, pasteurizing milk and things like that. We've done a study that found that companies could halve their energy demand. This is the case for German companies. This represents a third of the total industrial energy use. And the good message is the economic output remains the same. In the end, this energy cost savings are strengthening those companies. Most of the potentials are paying off in less than 3 years. And 100 terawatt hours here are attributed to reusing excess heat, heat recovery, and integration. And I also figured out when talking about process heat, people associate waste heat, but waste heat or excess heat, this is what is a byproduct or what's left over after manufacturing processes. And but of course, you can also use it again and recover it in your heat process or give it to third parties. Next slide, please. So how we are getting there, as I've pointed out already, it differentiates a lot on the temperature level. So we see the highest economic saving potentials in temperatures below 100 degrees Celsius. We even learned from our member companies that a lot of companies, like, for example, dairy production, they are producing steam without needing steam to pasteurize milk, for example. So this is why you have here very big energy saving potentials. The higher you get in temperature, the lower those economic saving potentials get. And of course, the measures to take are varying greatly. So, for example, in the higher temperature ranges, it is a lot about process conversion, for example, replacing steam crackers by how to say, so you can buy innovative materials, and in other fields, it's more about like heat recovery, waste heat utilization. So it's very much depending on the individual process and very much about the temperature level. Next slide, please. There is, on parallel, an enormous market potential because a lot of those technologies involved are manufactured in Europe. And this field has developed more dynamically than our economies in a whole. There is great potential for the future, up to factor 22, which could mean 1 million jobs in the efficient and clean process heat industry in Germany alone by 2050. And this involves in jobs, of course, installation, consulting services, heat pumps, and the field of heat pumps is even more dynamic. So if you compare it to other industries, process heat is already on par with wind and solar industries, but this is really a field that could go up and is on its rise. Next slide, please. So, we have to secure strategically our competitiveness here. We see that the international competition is growing, while EU exports grow by 7% per annum, and the EU holds 30% of the market. It's already losing its share since 2010. So you can see the comparison here, and we have to prevent the trauma we experienced in the solar industry to not be repeated. And this is why policy initiatives are needed to secure and leverage competitiveness. And what I also have to add here, it is a lot about independence from gas imports, from energy imports from Russia, the United States. And those are technologies where we are independent and we can use them to become more independent from energy export. And this is the great chance we should not miss and a great resource we have as Europe. Next slide, please. So, and there are some companies already using those opportunities. This is one of two which I would like to present to you. This is a typical German Mittelstand company in the Sauerland, the home of Friedrich Merz. And they exploit their excess heat potential through internal warm water grids and heat pumps. So they have two levels of temperatures involved. They have a hot water network they are using for drying, heating, degreasing, and then they have continuous annealing furnaces on a higher temperature rate. They are using to produce their tubes they are producing, and they are reusing the waste heat from the cooling circuits of the foundry, and also the waste heat from the compressors. And they are changing the energy carrier by electrification of the continuous annealing furnaces, and they're also installing heat pumps to decarbonize their hot water network, and investing 3.1 million, which is a lot for such a medium-sized companies. So they are really committed. Next one is a German company which is known on internal markets, big listed on stock exchanges, Covestro, manufacturers of chemicals and basic materials, with 18,000 employees, and they have issued what they call an energy efficiency portfolio, and we find this quite interesting because this is representing a cascade which is starting with energy efficiency first to tap the energy efficiency potential, then integrating excess heat into their production processes and electrifying where possible. For the rest, they are using biomass. Of course, they are expecting to use hydrogen. So they are located where the big hydrogen pipelines are planned to be built. And they're also using CCU. So, for example, they are producing plastics used in mattresses. And they are testing to use their excess of carbon to reintegrate it into their processes. But the interesting thing is it's not greenwashing. They are starting with energy efficiency first. Maybe you can return to the last slide shortly. So I don't want to go too much into detail here. So they're very innovative, but what they have achieved by doing so is a reduction of their specific energy consumption by 40% since 2005, and by 2030, they want to reduce specific energy consumptions by 20% compared to 2020. And this is what they are trying to achieve mostly by reducing waste heat. Next slide, please. So politics have to act now. This is starting in Germany to enforce the energy efficiency principle and the energy efficiency directive. So there has been a deadline by last weekend, which Germany did not deliver to. Second part is about making electrification efficient and affordable. So we still have a energy price rate which is not favorable for electrification yet. But at DENEFF we are asking to couple this with strong energy efficiency policies to avoid subsidy spirals. Third point is to strengthen the EU industry and to unlock the markets and to tackle delayed grid access, which is a big problem to many companies, that they are not able to get grid connections they need for electrification in a timely manner. The second is to mandate waste heat and cold recovery. So it's not mandatory for major emitters yet to reuse it. So this would be needed as well, and to integrate this into spatial planning and industrial transformation. And the last point is the market of energy companies. So we need companies which are helping other companies to become carbon neutral, so-called ESCOs, energy service companies. And what we are seeing in Germany is that we don't have fair and stable market conditions for them, and we have to remove those market barriers to them, and also to promote schemes which are helpful to grow this market, to make decarbonization of electric processes a business case. Next slide, please. So, and in the end, this is all about making this issue as normal as these products are, and energy efficient and fossil-free production should also be a daily matter in politics and public discussion. And I'm happy to discuss with you all and work together to make our industry fit for the future. Thank you very much.
Thanks a lot, Christian. Vielen Dank for this really great presentation. We will shortly leave you here and see you again at the Q&A session. Thank you for really highlighting the importance of tapping into the efficiency potential of industries and all the economic benefits and all the other benefits for society that we could reap out of this. We should integrate indeed this excess heat, and how to do this. Well, this is the purpose of the next presentation that will tell us now what is the right technology basically for any situation for industries. So I will now invite to the stage Piero Colonna, who is our partner as well at KCORC, the Knowledge Center of Organic Rankine Cycles. We are very delighted to welcome Professor Colonna, who is also Chair of Propulsion and Power at Delft University of Technology, where he also directs the Aerospace Engineering Graduate School, holding degrees from Politecnico di Milano, Stanford University, and a PhD in Energy Engineering. He has extensive expertise in advanced energy systems, heat pumps, and turbomachinery. Before joining TU Delft, he held academic positions in Italy and has since led pioneering projects on renewable power systems and waste heat recovery. So, Piero, the floor is yours to present to us how to harvest thermal energy and what is the right technology for any situations. Are you with us, Piero?
I am. Here I am.
There you are. Perfect. So please, the floor is yours. I will be intuitively moving the slides for you.
Yeah, thank you, because I cannot take control, apparently. It says that control is disabled for some reason. Anyway, here I am, happy to contribute to what will be said by all these very nice colleagues. We are all very much focused on trying to improve the situation with respect to waste heat recovery. And it's something I've been working on for a good portion of my career, very enthusiastically. Here is the content of what I'm going to tell you today, so please move on. I will tell you about these technologies and how do they work, assuming that, of course, not a lot of technical knowledge is among the audience, so I will keep it quite simple and hopefully entertaining. I will tell you about the enormous potential of this resource, that it's invisible. Thermal energy is just sent to the atmosphere, and therefore probably public awareness is not there. But we academics have studied that, and we know there is an enormous amount of that just waits for us to use it efficiently. There are technologies to make use of that, and I will briefly cover when used one on another, and the statement there is that they are not competing. There are situations in which one is better and others in which another is better. And then I will conclude my talk by telling you what is needed in our opinion, and I will present very shortly a very interesting example. Next slide, please. So here today, I will tell you briefly about organic Rankine cycle power plants and heat pumps. You see what we call the process flow diagram on this slide, the ORC on the left and the heat pump on the right. And even if you do not know what these symbols are, you probably immediately notice that the two drawings are very similar, apart from some small details. On the left, you see a trapezoid, which indicates a turbine, and on the right, you see a trapezoid that indicates a compressor. And the difference is the arrows that depicts how the fluid of the system circulates. This means that the working principle of these two machines is very similar. In the case of the ORC power plant, as you see from the simpler diagram on the right, is generating electricity, And on the right, you see for the heat pump, the objective of the machine is to upgrade heat, basically taking heat at a lower temperature and bringing it at a higher temperature. Now, this all is made possible by exploiting heat that is otherwise discarded. On the left-hand side, you see that acronym PHE, which means primary heat exchanger, and that is where the heat that is normally wasted is absorbed by this machine that is able to generate electricity. And on the right-hand side, you see the low heat temperature primary heat exchanger. And on the right-hand side, you see that this heat is delivered to a process at higher temperature. Next slide, please. So with this association of which I'm part of, the Knowledge Center Organic Rankine Cycle, we have run a study to identify all the sources of waste heat in the European Union countries. And you see those dots there that are colored with different colors corresponding to different industrial sectors. And the magnitude of the circle corresponds to the amount of heat that is dissipated. This is actually rather difficult data to collect, but still an effort has been done, a scientific effort. And I'm very happy to tell you, for those of you who do not know, that finally our countries are busy making databases about the amount of heat that is dissipated. A very good example is Germany, that has done that and is doing that quite systematically. And I am entertaining discussions with the government of my own country, the Netherlands, to do the same. We have something similar. We want to bring it at that level of accuracy. Next level, please. Next slide, sorry. In this analysis that we have run, of course, when it comes to the technical problem of recovering heat, it is extremely important also to know at what temperature heat is available. And there would be a long discussion again on how to estimate these numbers correctly. It is not easy at all. Here we have divided these thermal energy sources in percentage availability per temperature range. And you see there that there are quite some differences among the various sectors. The good news is that we have a technology for each of those temperature levels, depending, of course, on the boundary conditions, which are very diverse, depending on the financial situation, the geographical situation, and so forth. This is just to tell you that we are studying actively these things, and there are solutions for that. Next slide, please. In this exercise that we have done, we have looked at the problem, let's say, from the point of view of converting that energy from thermal energy to electricity. We have used very conservative assumptions. So not all the energy that is discarded is depicted in this table, but only the energy that we thought would be recoverable with RC power plants in a realistic manner. And please keep in mind that we do not have good data even on the total amount of energy that is dissipated. With this very cautious approach, we got to the conclusion that it would be possible today to install RC power plants for a total of almost 19 gigawatt of electric power. That is therefore more or less equivalent to 19 nuclear power plants in EU countries. Click, please. That is the equivalent to the yearly electricity consumption of two highly industrialized countries like the Netherlands and Denmark. And this should really ring a bell, because first of all, things will change in case hydrogen will be introduced as a fuel. But we know for sure that all these processes will need heat, and with ORC heat recovery, we can generate electricity even with those fuels that is completely CO2 neutral. Now, some examples of sources of wasted heat is, of course, in the petrochemical processes, material production, as my colleague said before, metal, cement, and glass. There are a lot of mechanical drives around, for instance, in the oil and gas industry. Those engines waste an enormous amount of heat. There are incinerators and so forth. Click, please. Now, when there is the possibility of recovering heat, this is the pyramid of what makes sense. Of course, the first thing that should be done is to avoid it or to use it directly in the process. If there is heat utilization locally, it makes sense to upgrade it with a heat pump or to generate cooling effect with the sorption-based processes. And if nothing else is possible, use an ORC plant for electricity generation. Click, please. In that case, we should keep in mind, though, that electricity is extremely valuable as an energy form because it's transportable, easy to integrate in any process, and very flexible. You can easily sell it on the grid. Now, click, please. Here you see some basic data about the two technology. Heat pumps can make use of heat in the form of cold water, air, or warm water. Technology today allows you to upgrade heat from almost 0 Celsius up to 200 or 250 Celsius by adding steam compression, and with power capacity from hundreds of kilowatts to more than 50 megawatt. Let's keep in mind that all these technologies are modular. ORC power plant, warm water or hot gases can be the hot sources. You can convert that into electricity economically from 120, say, up to 500 plus, and with power capacity from 100 to 50 plus. The advantages of these two technologies are very similar. They are thermal source indifferent, efficient. Please go on quickly because I'm out of time. Proven, can be cost effective. They are flexible, as you have seen, in terms of temperature and heat capacity. Modular, in case of ORC, they do not need water cooling. They're fully hermetic, no makeup water needed. Small footprint, full automation. They can serve as a grid service, so solving part the possible grid problems of the future. And they are easy to locate because they are within industrial environment already. So they can greatly contribute to the resilience problem of Europe today. I told you that I would tell you of an interesting example. I was there when the wind energy revolution, so to say, started at the end of the 80s, 90s. And there were articles that were saying that it would never happen. It would never be economically feasible. This chart, which is related to Europe, shows exponential growth of wind energy. How was that possible? In my opinion, it was possible because our government consciously decided to kick it off. This is what we need today. And I hope people in the audience will make notes. We have written an interesting white paper, which is freely downloadable from our website, where there is a lot more than what I told you. And I would be grateful if you consider downloading it and reading it. Thank you very much.
Thank you very much, Piero, for this very complete presentation and pedagogic. Thank you very much. I think it clarifies also the difference between both technologies. I see there are questions coming up, hands raised. Please write in the Q&A if you have any question, and we will surely let you on mic during the Q&A session later on. Piero, we see you in a few minutes. We're indeed a little bit running out of time, so I will try to catch up on this. I would like now to welcome our female speaker and expert, Laura Alonso, who's a senior researcher and project coordinator at Tecnalia in relation to Push to Heat EU project. So Tecnalia is a leading Spanish research and innovation center coordinating the EU project Push to Heat, focused on advancing industrial heat pump technologies. Laura Alonso is a chemical engineer from the University of the Basque Country, specializing in energy systems and fluids thermodynamics, with over 10 years of experience at Tecnalia's Efficient Thermal Energy Systems Group. She develops research and development projects on energy efficiency and thermal energy systems, focusing on industrial decarbonisation and advanced heat upgrade technologies. All this to tell us but now more concretely about a case study on heat pumps, after which we will check on a case study on ORC. So Laura, please, the floor is yours, and I'll do my best to move your slides intuitively today.
Okay, thank you very much, Rachel. I will start my presentation then. So it's focused on the practical industrial implementation of high temperature heat pumps. And concretely in this case, it is in the scope of a European research project called Push to Heat. Next slide, please. Okay, so in Push to Heat project, we have different kinds of objectives. On the one hand, we have the technology-related objectives, mainly focused on the design and optimization of 4 different heat upgrade technologies. But also we have market and business-related objectives. We want to push forward the market potential by developing new business models and actions towards technologies market deployment. This will be done mainly by the demonstration of 4 full-scale pilot plants in different industrial applications. And we have different ranges of temperatures for the waste heat sources between 40 and 90 degrees Celsius. For the upgraded heat supply to the industry between 100 and 160 degrees, and also for the system size or upgraded heat capacity between more or less half and 1 megawatt of installed power. Okay, which are the technologies of push to heat? Here, I would like to highlight that we have 2 different kinds of heat pumps in this project, the electrically driven heat pumps and the thermally driven heat pumps. The electrically driven heat pumps have been introduced before by Piero, but we also have different kind of systems. So for the electrically driven heat pumps, we have 2 demo sites, demo 1 and demo 2, by the manufacturers SPH, Sustainable Process Heat, and by Canon Bono. And for the thermally driven heat pumps, we have 2 different technologies within this group, the absorption heat transformer by BS Nova in demo number 3, and the thermochemical heat transformer by Q-Pinch in demo number 4. Okay, what is the main difference? What is the main difference between the electrically driven heat pumps and the thermally driven heat pumps? In the first group, we have 2 temperature levels. So we need an input of waste heat at a medium to low temperature level, and by the use of electricity, we will upgrade this heat to a higher temperature level. On thermally driven heat pumps, on the other hand, we have 3 different temperature levels. So we need an input of waste heat at a medium temperature level. We upgrade the heat at a higher temperature level, but we need to dissipate around half of the input heat at a lower temperature level. And this requires a much lower amount of electricity consumption in the system. Next, please. Okay, so push-to-heat demo sites are located in different European countries. We have demo 1 in Germany, demo 2 and demo 3 are located in Italy, and finally demo 4 is located in Belgium. And now I will explain each of them one by one. Okay, demo number 1 consists of an electrically driven heat pump, high temperature heat pump with piston compressors in the paper industry. This heat pump is installed in Weissenborn in Germany in a paper mill of Felix Scholler. The participants of this demo site are the plant, the owner of the plant, Felix Scholler, the manufacturer of the heat pumps, Sustainable Process Heat, and a research partner, we have the Fraunhofer Institute. Next, please. Okay, waste heat is taken, in this case, from the paper rolling process itself. So from the paper machine, we have humid air at a medium temperature level coming out of the machine, and we take advantage of this waste heat to feed the heat pump. Then, by electricity consumption in the compressors, we upgrade heat at a temperature level of around 123 degrees, and the upgraded heat comes in the form of direct steam from the machine, meaning that the condenser of this heat pump is also a steam generator itself. Here you can see some scheme of the complete machine with all the components included, and below some pictures of when the machine was finishing the manufacturing process, and of the machine already installed in the plant inside the container. If you want to check more facts on this technology, you can always check the technology fact sheet of this and the other technologies of push-to-heat project in the website, and I include here a link. This heat pump is providing around 1.2 megawatt of upgraded heat, and here just some values, reference values for the efficiency and the savings. Taking into account the temperature lift that we have, the COP electrical is around 2.3, and with a reference value of 4,000 hours per year of operation, we will have expected values of primary energy savings of 2,400 megawatt hour per year and CO2 savings of around 230 tons of CO2 per year. The machine, as I said, is already installed, as you can see in the picture, and the commissioning process is ongoing. The next one, please. Okay, the second demo site is also an electrically driven high temperature heat pump, in this case with screw compressors, installed also in the paper industry, but in this case in Italy, in Guarcino. The participants of this demo site is the plant, Cartiere di Guarcino, Canon Bono Energia as the engineering company, and also designer and manufacturer of the high temperature heat pump, and the Politecnico of Milano as the research partner for this demo site. Next, please. Okay, which is the waste heat in this case? We have waste heat from the cooling water of the cogeneration plant present in the paper mill, and we upgrade heat firstly in a first stage at a pressure level of around 1.7 bar. So this heat pump is producing steam directly as well. This means around 115 degrees, more or less. And then the pressure level needed in the plant is higher. So we are combining the high temperature heat pump with an external mechanical vapor recompression system, which is a steam pressure upgrade system, which needs electricity to run as well. And the output is steam at 6.5 bar, which is around 162 degrees. The upgraded heat capacity in this case is around 860 kilowatt. And some reference values for the efficiency. We have electrical COP of only the high temperature heat pump is around 5, because the temperature lift in this case is lower, but taking into account the whole system, so including as well the mechanical vapor compression system, we have a combined COP of 3. With a reference value of 7,000 hours per year of operation, we will have primary energy savings of around 3,400 megawatt hour per year, and expected CO2 savings of around 700 tons of CO2 per year. The high temperature heat pump, you can see the scheme. We don't have pictures of the machine because it's being constructed in this moment. The idea is to finish the manufacturing transportation to the plant and installation within this year, and start the commissioning process at the beginning of the next year. Next, please. Okay, we continue with the third demo site. In this case, we have a thermally driven heat pump, the absorption heat transformer, installed in the same paper mill as demo 2. So we will have one paper mill with 2 demonstrators, an electrically driven and a thermally driven heat pump. And the participants are the plant, Cartiere di Guarcino, again, Canon Bono as the engineering company for the whole integration, BS Nova as the manufacturer of the heat transformer, and as the research partners, ourselves, Tecnalia, and the Technical University of Berlin. Next, please. Okay, the waste heat source is just the same as in demo 2, the cooling water of the cogeneration plant. This is around 85, 90 degrees Celsius. And in this case, we also provide steam, but not directly with the heat transformer. So the heat transformer produces hot water, and externally with a flushing system, we are producing in a first stage low pressure steam at 3.3 bar. This is around 137 degrees. But then we need to upgrade this pressure again. And in this case, we are using a thermally driven system, a thermocompressor, and we upgrade the pressure the same as before until 6.5 bar, and making use of high pressure steam already available in the plant. We need to dissipate heat at low temperature level as well. This is around 20 degrees. And the upgraded heat capacity in this case will be around 340 degrees. Okay, you can see a picture of the manufactured heat transformer on the upper part, and on the lower picture you can see the whole system, the heat transformer and the steam generation module already installed in the Italian plant. Some reference values for efficiency. When we are talking of thermally driven heat pumps, we normally refer to the thermal COP. This means the amount of upgraded heat we get divided by the input of waste heat introduced into the system, and it's around 0.48. And if we refer to the electrical COP of only the heat transformer, it would be around 35. And if we include as well the pumping system between the EHC and the SGM, it will be a little bit higher. With the same operating hours per year, we can expect the primary energy savings of around 2,800 megawatt hour per year, and CO2 savings of around 500 tons of CO2 per year. This, as you can see, is already installed, and we are as well in the commissioning process. We have been there sometimes, and we need to travel again to Italy to continue with the commissioning process very soon. Okay, next one, please. Finally, we have demo 4. This is the thermochemical heat transformer by Q-Pinch, which is installed in the chemical industry, concretely in the plant of Borealis in Belgium. And in this case, it was a system that was already built before Push-to-Heat project started. So it is not constructed from scratch in the project like the rest of the demo sites, but they will use this system within Push-to-Heat to test it in a very wide and different ranges of temperatures and capacities. Okay, next one, please. Okay, they are taking the waste heat from an exothermic reaction in a chemical reactor around, well, in a range, as I said, between 75 and 140 degrees, and they produce upgraded heat in the form of steam as well, in a range of temperatures between 110 and 185 degrees. The upgraded heat capacity as a reference is 1 megawatt, and here we don't have primary energy savings or CO2 savings calculation because, as I said, it will test different ranges of temperatures, heat capacities, etc. So it's more of a testing facility for demonstrating the technology. Okay, next one, please. Okay, if you want more information on Push-to-Heat project, you can visit our website. You can follow us on the social media, especially on LinkedIn. And also, if you are interested in receiving periodic information on the progress of Push-to-Heat, you can always join our stakeholder network, and you will receive periodic information on the advances of the project. Now the project is in a very interesting point because we have many demonstrators running and in the commissioning process, and soon we expect to have real data of these demonstrators. Okay, and next one. And finally, as a summary, I would like to highlight the importance and potential of high-temperature heat pumps for the electrification of industrial heat. So high-temperature heat pumps can provide a higher energy efficiency in the industrial process, making profit of available waste heat at low to medium temperature levels. And I would like to highlight this energy efficiency first principle, but also at the same time, they contribute to the electrification of the industrial heat demand, aligning well with the electrification action plan in the industrial field. Several barriers exist for their implementation, such as the grid power access for electrification. This is a problem that some industries are facing when trying to upgrade their installed power for electrification purposes. Also, the electricity to natural gas cost ratio. This is dependent on each particular country, and the more critical, the higher is the temperature lift. Therefore, always a case-to-case analysis is needed for economical feasibility, and also the need for skilled professionals. So what can be done? Providing clear long-term regulatory alignment at European and national levels, also broaden the knowledge among technicians, engineers, and project managers, support demonstration projects such as this one, as push-to-heat, promote the sector and process-specific approaches in order to facilitate successful high-temperature heat pump integration, and also promote the subsidy programs such as energy efficiency certificates or the latest Innovation Fund pilot action for industrial process heat decarbonisation. Okay. And that's it. Thank you very much. I will be happy to answer any question you have.
Thank you very much, Laura. This was really very, very interesting and very concrete as well, real-life examples and industrial applications. I'm sure it will trigger some remarks or questions that we will come back to very soon. We have one more presentation here, so I'm going to
Michelle, I fear we can't hear you.
Thank you, Roberto, so much for letting me know. I will start this again, which was actually quite good because there are so many things to say about you that we could take all the time in the world for it, but I will try to keep it short as we are also running a little bit out of time. So I will repeat myself. So Roberto Bertanzi, welcome. Thank you for joining us. And you are the technical product development expert of TurboDen. And you will present to us, similarly to Laura, the case study, but on ORC. You are... So TurboDen, is an Italian company of the Mitsubishi Heavy Industries Group, specializing both in ORC and heat pumps for heavy industries. You are the technical product development, which means like you are a mechanical engineer as well, graduate from University of Brescia. You have extensive experience in both technologies, systems, commissioning, and performance optimization for them. You also currently lead TurboDen's decarbonization initiatives through the advancement and application of large heat pump technologies and their integration in different sectors. After a distinguished period dedicated to ORC application, you now provide us strategic support for the implementation of large heat pumps in industrial processes. And now we are very happy to hear you about ORC. So tell us please about them and what are the concrete industrial applications for them. The floor is yours, Roberto. Thank you.
Okay, thank you, Rachel, for the introduction. Let me say that I approached the conversion of heat into electricity thanks to Professor Gaia, the founder of TurboDen, at the early stage of the ORC technology. And as you said, I was dealing with ORC for a long time. We have now more than 400 units in operation here. But since a couple of years, I switched to the heat pump. So I have a double, now I'm talking to you about ORC and heat pump in my presentation. Let's say that the electrification and the heat recovery are a fight with the thermodynamics laws and with the business plan. And now I will introduce the showcase of Ori Martin, a large steel mill in Brescia, which is a high intensive energy process, the production of alloyed steel. And this is also a returning customer, proving that the fight with thermodynamics and business plan has been won. So this steel mill has basically a heat recovery system installed in 2016, generating steam. The first step of the project has been to convert the steam into electric power thanks to the ORC turbo generator in 2017. And since last year, we also added a large heat pump. Now we can go to the next slide. I will spend some more time on this slide because this is the concept of the heat recovery in Ori Martin. We have in the gray area, we have the electric arc furnace, which reach with temperature ranging from 300 to 1600. And we have an exhaust going to a chimney, to a filtering system and a chimney. And the the melting pot cooled by water with a wasted heat. And the first step has been the introduction of the steam generator. And this steam is converted into electricity in the green area with an ORC manufactured by Turboden, producing up to 2 megawatt electric power. And we don't use directly the steam because it is not convenient. It is if we consider the maintenance cost and all the technology practical solution, it is easier to adapt to an intermittent process with the ORC technology, with a binary plant, instead directly expanding the steam into a Rankine cycle, in a steam Rankine cycle. The next step, because it has been in the winter season, to recover and have the possibility to recover also the cooling water heat and upgrade from 70 degrees C to 90. This temperature can range from 85 to 105 and heat the Brescia municipality. Brescia is a town, industrial town, where our company is based, with about 2,000 people living there. And 70% of them are connected to the local district grid, to the local district heating. And next slide, please. So the main point to consider in a heat recovery project in the steel mill are the intermittent production. So it is not like a geothermal plant running all the year long at the same heat source temperature. We have fluctuations, and this is perfectly coupling and matching with the ORC technology, which easily adapts to in the whole range from the partial load to the overload condition. In this scheme, the ORC works mainly in winter, because it is the ORC is stopped in winter. Sorry, and while the ORC is working in summer when there is no heat demand from the district heating. The opposite in winter, the heat conversion is diverted to the large heat pump. The project challenges are to deal with the dust, with all the particle in the flue gas of the furnace, the intermittent operation, and also the normal planned maintenance. An electric arc furnace is not working 8,760 years long, but it has a lot of stops and starts. So it is extremely, we realized immediately that the most important thing is to have a flexible plant, easily starting and stopping and adapting to the changes. If you can go to the next slide, thanks. Okay, just I mentioned some nominal data of the two project. DORC can produce up to 2 megawatt. So also some overload. And we have a siloxane fluid as a working fluid. Now it is quite standard for us, and also hydrocarbon can be used, all the organic fluids. But what is interesting is the range. So we have a neat source, which is the steam at 16 bar 180 degrees C, and we produce our this is the design data, but we could even exceed this value. The large heat pump on the right side has a completely different cycle, so in the opposite way as Piero mentioned at the beginning. So this makes more easy now to read those data. In this case, we use electric power. We use the 485 kilowatt to produce thermal power, those 4 megawatt, enhancing the temperature of the heat source from 77 to 90. I also added the full range from 85 to 105. And the COP, the coefficient of performance, so the ratio between the thermal power and the electric power, ranges from 8.6 down to 6. Of course, if we increase the temperature, the COP decreases. Next slide, thanks. So now I want to show you the both cases. So the ORC has a classic organic Rankine cycle with regenerator. And as I said, I emphasize once again the flexibility and the very low maintenance. So thank you. The performance covers the full range from a few kilowatt, so from 300 kilowatt over 2 megawatt, with an efficiency that is not varying that much with the load. Next slide. Thank you, Rachel, for the next slide. Okay, this is a 1 week. Sorry, go back. I just wanted to show you what it means intermittent heat source. So it is important, and I remark once again that the ORC adapts to the changes. Where you see there is no production, it is not a fault of the system. It is just a normal maintenance. So the ORC produces around 4 gigawatt a year, and allowing to save 1,000 ton a year. And now this chart is a little bit tricky, but the efficiency is on the right side, the blue dots, and the red on the left side, the red is the electric power. So let's go to the heat pump. So the heat pump is the opposite cycle. And I remark again, this was a returning customer with a returning project. This heat pump we will start on Monday after the summer period. So we are close to the new startup for this thermal season. I can show you briefly, and I will try to recover as much time as possible. So it is quite interesting, the startup. The startup of the heat pump requires only a few minutes if everything is hot. If we have already preheated the lubricant and heat exchanger are ready, we can go in operation in a few minutes. And this makes the heat pump perfectly to be coupled with flexible system of energy management. Next slide, please. Okay. This is a 2 weeks chart proving with the first chart is the nominal the outlet temperature. In this case, we run for a long time at 88 degrees C, according to the steel mill thermal power. Again, where you see missing production this was a normal melting pot maintenance, and with the COP in the range of 8. Next slide, please. So the steel industry is really an energy-intensive process with a great potential, with all the together with glass and cement. And this project in Ory Martin is a showcase because it's a flexible plant. It proves that the fight with the thermodynamics and the business plan can be won thanks to the EU support developing technology. So really, my contribution is mainly to show you This can be done. We have an example. You can visit this plant and we can make it real. The important is to within the EU institution and the best technology companies we have here in Europe to exploit this potential. I will be glad to answer all of your questions in chat or later on, if any. Thank you, everybody.
Thank you very much, Roberto. And you can stay with us because now is the time to answer questions indeed and for the audience to join us. So I would just like to invite first all the speakers to come back on stage, please, and on camera. And thank you all for your great presentations. I will now give the floor to Gianluca. Gianluca is the Senior Associate at the European Climate Foundation. He was going to moderate our Q&A and our Slido. He's based in Rome. He develops partnerships to decarbonize heavy industries in Italy, who holds a master's in energy engineering from the Polytechnic of Milan and an MBA in the business school WHU, and has experience in manufacturing operations and sustainability management. So another great expert with us today, and I give you the floor to manage the Q&A session now.
Great, thanks a lot, Rachel, for the intro. Thanks also to all of our speakers for the very insightful presentation. We had already a few questions in the chat, but also feel free to raise your hands and I can give you the floor to ask directly question to the speakers. So looking at what we have already in the chat, probably Piero, I'd like to start from you because there were a few questions and a bit of interest in the ORC technology, and actually what I saw there were really like practical questions. So what about the basically the readiness of the technology, the payback time, but also let me expand a little bit on that because you showed an enormous potential. So you showed that, for example, refineries, they offer like a huge potential there, but still, I don't know, there's something which is holding ORC back. So it's not like a super widespread technology. So what is holding back the technology and what should we do to make it adopt a little bit faster?
I can give you my take, of course, which is a take of a university professor, which means there are probably also many things that are related to the industrial world that I'm not fully aware of. But the first answer that comes to my mind is that, of course, the profitability of ORC power plants depends a lot on how much the electricity that is generated is valued and the energy as a whole. And we know that the value of electricity depends on a lot of factors. That is why I also call in our policymakers, all the industrial sectors for which energy is extremely cheap have very little incentive to make good use of the energy. So that needs to change. This is something that we need to hammer more and more if the final goal is a benefit of society. And of course, the problem is much more complex than that. You also asked about the maturity of the technology. The principle was invented in the half of the 1800s. So in the mid of the 1800s, the principle has been known for a very long time. Organic fluids have been used a few years later already to make machines. Very successful applications of RC technology started already in the 70s, the 80s, geothermal power plants. And as my colleagues mentioned, in waste heat recovery, it's more recent. But as far as I know from reliability data that some companies shared with us, the reliability is extremely high. I do not see technical problems there. Of course, nothing can be generalized. It depends a lot on the conditions for the installation. But I see as the main obstacle still favorable economic conditions.
Okay, and what would you say is the typical payback time for a new project? Do you have this kind of information?
We have scattered anecdotal information about it because, of course, these are data that are difficult to obtain in the public, but it varies a lot. It can be very short, 2-3 years. We have seen that. Yeah.
Lovely.
And let's not forget that these power plants last for 20 years, at least.
Good, thanks, Piero. There were also a couple of questions on other technologies, and maybe I can turn to Laura for these, because I've seen they have many technologies in there in these pilot projects. But basically, there were a question about energy storage, but also mechanical vapor recompression. If there's space for these kind of technologies to work together with the ORC and heat pump. So if you see this already happening in some places, or if you see this something else as a, let's say, different pathway.
Yes, of course, the integration of mechanical vapor recompression systems is something that we are already seeing for waste heat upgrade directly with steam, just the mechanical vapor, or combined with the high temperature heat pumps, as we saw in one of the demo cases of push to heat. These are systems that are more known in some industries. As some of the comments here in the chat, we have very high capacity systems already installed, but also for lower capacity systems, such as some lower capacity high temperature heat pumps. The combination and the integration is being analyzed, and in certain cases is very interesting. Yeah, instead of having a very high temperature lift in the high temperature heat pump itself, you can combine this with a mechanical vapor recompression system. And the possibilities for integration are very wide. And I would like to highlight that always a case-to-case analysis is needed, and we need skilled professionals that are able to make this analysis and to get to know which would be the best in each of the cases. And also the energy storage, I think, it is getting more and more important each time for letting flexibility opportunities to the industries in order to adapt to variable electricity prices, and in order to optimize this waste heat upgrade as well with combined with the high temperature heat pumps.
Okay, thanks a lot. And still maybe on staying with you, Laura, because I would be interested in let's say the human factor, let's say, just understand if this pilot project, how they are perceived by basically the operation people, so the people in the factory. Are they happy with this solution? Do they let's say, are they easy to operate? Do you get a good feedback from the people working with this technology every day?
Mm-hmm. Okay, well, I can answer only partially, because the machines themselves are not still running completely in a continuous way, because we are in the commissioning process in 2 of the demo sites, and the third one is not already installed. But the experience so far is being very good with the plant owner and operators. Yeah, they are quite happy to learn about these technologies. They are very involved in the commissioning process in order to get to absorb this knowledge and to be able to operate the systems correctly and hopefully successfully. And let's see when we have them completely running, if the feedback is as good as we have right now. But we will see in the near future. Thanks.
Piero, you want to comment on this?
Yes, I just wanted to briefly comment on the human factor, because I have a past as an energy engineer, trying, to sell plants and to build them. What I have noticed, talking at that time with customers, is that one of the problems, and I'm sure my colleagues in the OEMs making these plants know very well the problem, is that you get to a certain level and then the customer will start saying, yeah, fine, but I make X, fill in the blank, cement, steel, paint, whatever, and not electricity. And that it's a big psychological problem, because even in cases in which it makes sense, then a lot of questions arise and it's very difficult to bring it home. So that is why I think some creativity in the business models should kick in, and policymakers should really intervene, at least to kickstart what I think could be a revolution in Europe.
Yep, very good point, Piero. We also hear some resistance from the industry when it comes to, not making a product or making a commodity, but basically trying to sell a service or produce electricity. This is not something that they think they should do, but actually it's actually a possibility to save money or to create new additional revenue streams. And on this, maybe I'd like to hear also from Roberto, because what's happening in Ory Martin is actually up and running. So just trying to understand if, how it was perceived by the company. I mean, how did it start, I would say. And also there's a specific question on the example you showed us, Roberto, asking can be done to make the project a little bit more economically viable, because I guess there was like a big capex involved in this project, because you had like 3 different systems, one basically cascading the next one. So how was it possible to make it a bit more easy to start?
Thank you for the question. I think that first of all, in this specific case, I think it is the attitude of the company owner. This is a private company, despite it's a large one. So I will mention the owner mentality, because that's not only about money. So then we can start to discuss about all the other things, but basically it's an attitude. Then the EU support and the technology readiness is important, because the ORC payback has been very short. It is not important to say 5 years, 6 years. We are not in a bank. We are not banker, but we are technical people and looking to the big picture. I think that the heat pump is a little bit different. It's a less profitable business as a first tentative. So the first ORC recovery in Ory Martin has been a very better than expected. It was designed for 1.88 and usually works more than 2 megawatts, so everything went well. The heat pump is more tricky and difficult, but this is the apprentice curve. So the readiness of the technical solution for very large heat pump involving sealing system, high speed spindle, this has to be improved. And the very first solution in Ory Martin has been let's find the most reliable system, don't look at the payback. So to answer your question, I think this was the first heat pump. We have 400 ORC in operation and 2 heat pumps in operation. While I'm talking, we have a plant also in Finland with 12 megawatt at full power producing steam for a paper mill. But and this is better than Ory Martin. So the experience is, this was our apprentice curve, and we start to learn skiing from the blue slope, and then we will go for the black slopes. So this means that the more challenging project can reach a shorter payback as soon as we improve the technology and the solution. But we cannot go direct to the final solution in one step with the first project. So again, this was a good combination between the EU support, the customer, and Turboden, and also our competitor. I wish the best to everybody. The importance is to create a good humus where can grow an economy and a new, really a new way in Europe to produce energy.
Thanks.
Okay. Thank you.
And Christian, I'd move also to you, because there were a couple of questions. One about the role basically of the civil society, but in general, I would say, which kind of knowledge are we still missing in the ecosystem? And do you see that we need to create a little bit more, more studies on this? And also a second one was more on the system planning. in the sense that we have ETS2 coming into place, we have CO2 prices in general. And so how does this solution at factory level relate with what is happening in our energy system itself? Because at the end of the day, if the factories, industries become electricity generator themselves, that could also be, you know, an input and a feedback to the energy system. And what is more efficient, I would say.
Yeah, so maybe what you to start with what you ask on the civil society. So I have the impression when talking to civil society actors that what is waste heat, at least in Germany, is well known. It's not known in the broader public, but like environmental organizations know about waste heat, maybe because also this narration of there is waste and we have to prevent waste rather fits to ecologic organizations and others, or the idea of wasting something is always associated to something bad. So this narrative is working well. But on the input level of industrial heat and process heat, this is completely overshadowed by the discussions about hydrogen, about how to decarbonize industrial process direct emissions, not those process heat emissions. And this is still missing. The studies are there, at least for Germany. We have built up a profound database. I've showed you some data from this, but now our mission is to come from facts to fans and to build a fan base that also others in our ecosystem says, yes, process heat is key and we have to decarbonize it by energy efficiency, by changing the energy carrier. And then when waste heat is left over, let's recycle that. And that should be the narration known. Of course, this all reconnects to the energy system level, starting with grid access. And we have now a lot of dynamic in Germany with big electric storages, because there is a business case behind that by arbitrages. But this also creates new tension to the electricity system. And when you have like a ranking, so somebody just told me when you're talking to regulators, they have such a pile of ask to get electric storages connected. The second biggest pile is a pile of new data centers. And then there is a smaller pile of getting connections for larger heat pumps. So, and the question is what priority this plays in the electric system. And it's not just about the pricing. So when pricing is working and people say, okay, I'm ready to take the decision, maybe I also have some recycling from the ETS revenues in our programs. That's how it's working in Germany. So our ETS revenues also for ETS2 are recovered for investment programs. And then I'm ready to invest, but I don't get the electricity access. And this integrated way of thinking is not already existing on policymaker levels, because other topics, as I told you, like hydrogen, are dominating. So and this is also we have to work on as a community to get this integrated and say, okay, we have to start here. And maybe also give priority when we are talking about state aid to companies who say, okay, I'm about to electrify, I'm a front runner, and then to get this to a principle where who's the most ambitious in climate protection maybe gets the fastest access. So that could be maybe an idea, but that's a discussion which is definitely has to start, and also a competition of ideas how to get there, because all other industrial issues are also important, huh? So yes.
Piero, you had a comment on this.
Yes, just quickly, I wanted to tell policymakers in our white paper preparing that we have made an effort to look into policies, and then we have talked to the various actors. In my view, it is absolutely clear one of the problems of the European Union, directives are issued and then each and every country applies them in a different way. This makes it very difficult for OEMs to follow all the different laws and regulations regulations and so forth, and also very expensive. Really an effort should be made to make European regulation, well, on the one hand, more rational, and on the other, the same for everybody. If we really want to tackle this problem.
Yeah, and also stable, let's say, with long-term predictability. That's very important as well, to give confidence to the people to invest, I would say. And Roberto, last question to you, because there's actually two. One is about the efficiency level of the ORC systems. I mean, you said you have more than 200 installed, so you probably can give some good real life example. And the second one is about the implementation. So when you want to install one of these systems, how heavy is the construction work? How much piping you need to do? I mean, how heavy is the integration with the normal process?
Okay, thank you. Let's say first comment about the efficiency. Of course, the efficiency depends on the thermal input and output, but let's say that for application in a typical cement or glass ORC application, we are ranging between 20 and 24%. In biomass application, producing also heat, so combined heat and power in a small district heating on the Alps, the efficiency can be 18-19%. In a geothermal plant, cooling at ambient temperature with a heat source between 100 and 140 degrees C, the efficiency is much less. It can be 11-12%. So this is to give you a rough idea about the efficiency. The second question was about the construction and the effort. Let's say that standard unit up to 2 megawatt, it is possible to deliver a prefabricated ORC, install it in a very short time, and we can deliver it in 9 months. Since the concept of the project, in 9 months we can install the system, and that's it. In custom application, in special project, in very large project, is completely different. In this case, in some project we need to involve an EPC company, and the project can last 2 years. So the basic answer is, it depends. For standard application up to 2.5 megawatt, it's very easy. It's something plug and play. If you go above, you have to involve a construction company, and the project schedule has to be extended from 9 months to up to 2 years. We are now commissioning a plant in Dashur in Egypt. And this project is lasting. We are since, I think, 4 years, and we are now in a commissioning phase. So you can have everything. Okay. I see Rachel stopping.
Yes, so sorry, I have to stop you all with this Q&A. Unfortunately, also, we don't have time to go through the Slido, but you will receive the slides and you will be able to go through the questions that are related to the presentations that took place today. Without any further ado, I would like to invite to speak Paul Kenny, who is the Director General of the European Heat Pump Association and mechanical and energy engineer with a master's in energy, formerly policy advisor to the Irish Climate and Energy Minister. He played a key role in Ireland's energy transition. He previously led an energy agency, local energy agency of Ireland, and established an early one-stop shop for home energy upgrades. Now we're going to link the innovation to the politics and how this can feed the European Electrification Action Plan. Paul, the floor is yours to conclude on this webinar. Thank you.
Thank you very much. And sorry for the early mic. I was just very eager to get in. So thank you very much, everyone. It was a really interesting discussion. It took me back to some of my college days studying organic Rankine cycle engines. But what was really interesting, one of the things that I took away from it, I thought, Roberto, your comment about the fight with thermodynamics and economics, I used to always use a line that said when thermodynamics and economics align, you've got the energy transition. So it's good to hear it in a slightly different way. It's really interesting to look at the various different case studies. And I think one of the things that I see and hear all the time is the sheer scale of potential in the of industrial heat pumps. They're maybe at 1% of their potential right now in Europe, with the potential of 37% of European industrial energy use being applicable with today's technology, never mind future technology. So from that perspective, and that's really just the heat decarbonisation, not even the energy, electricity production from waste heat, which is another huge advantage. I think one of the things I'm going to try and keep my time down to 5 minutes, just because we're over time. One of the things that I see across the Commission is we have, so when just to bring in policy and politics of this, we have spent a lot of time in the European Heat Pump Association trying to bring this message into policymakers to maybe overcome some of the noise of hydrogen, as was mentioned, to really showcase case studies, to bring the opportunity of the industrial heat pump right into the centre of European policymaking. And we did succeed in getting DG Ener and Dan Jorgensen, the Energy Commissioner, to really highlight in his recent June 10-point plan energy efficiency the opportunity of industrial heat pumps and waste heat recovery. So we are starting to really put the industrial heat pump into the centre of European policymaking. It takes time; it's a slow-moving ship. So let's keep a pressure on. Another thing we do a lot in the Heat Pump Association is to try and network and develop relationships between our members and their end users. So we have worked on guidance with the paper industry. We've worked on guidance with, are currently working on guidance with the food industry, with individual large companies come to us with a variety of opportunities, and also with the Man-Made Fibers Association. Again, linking back up to the very beginning of the webinar, those plastics that we all wear are really important users of this technology, or will be in the future. The other thing we do in the association, and we've mentioned Push to Heat, but we work on a lot of European projects. We're starting another 3 on industrial decarbonisation on top of our existing 5. And they again support our members and industries convert from fossil fuels to very efficient industrial use of heat pumps. And finally, one thing I would like to maybe just highlight to everyone on the webinar today is we work very hard with the Commission on a new innovation fund around industrial heat pumps. So there's €1 billion for heat decarbonisation in industry, and it's broken into chunks for different technologies. A lot of it is for industrial heat pumps. I'll put a link in the chat. You can look at it. But that is the first pilot innovation fund for industrial decarbonisation. And if this is successful, there will be a lot more money to flow after it. And the idea is that this, my call to action for everyone today is to use that funding scheme to try and develop further and better economic opportunities for industrial heat pumps, deliver this, deliver projects into it, and more money will flow, because there is a very significant political need to support our European industries and their journey on decarbonisation, and I think it's really important. So that's my final point: is make use of the money we have managed to guide into the industrial heat pump sector. And without further ado, I think we're 3 minutes late. I'll hand back to Rochelle.
So much. Thank you so much, Paul, for this perfect conclusion, and also this great fund that you have the link of in the chat. I'm sorry we could not answer all your questions. There are way too many, and thank you for your interest. For this, we take the opportunity of this good energy to lead you to the next step of this webinar, which is a conference called similarly What's Next. However, here the focus is really more on competitiveness, energy security, and it will take place in person in Brussels. We will give you a bit more information. However, you can already register and join us to continue this discussion. If you have urgent questions you would like to get the answer of that were asked or unanswered today, please send it to us. You can email us at events, basically at ehpa.com, and we will .org, sorry, and we will forward your questions to the speakers. We have many events upcoming. All your organizations do. You'll be able to register to some of them and benefit from discounts that EHPA offers for you. So you can check this afterwards while the slides will be sent to you, as well as the recording of this webinar. Thank you all for joining. Thank you once again for the speakers for your great presentations and contributions. We look forward to seeing you again for the next event. And please, let's stay in touch and continue the discussions in different ways and forms and shapes. See you all soon, and bye-bye for now.